Thank you all again for coming. Welcome to the CITP seminar. We're just going to give everyone another minute to arrive. Ready, Kristian?
Uh-huh.
All right, let's go ahead and get started. Welcome to the CITP seminar. It's my pleasure to introduce you today to our speaker, Kristian Lum. Kristian is a senior staff machine learning researcher at Twitter in the Machine Learning Ethics, Transparency, and Accountability group. They call it the Meta group. Prior to that, she was a research professor at the University of Pennsylvania in the Department of Computer and Information Science, and the lead statistician at the Human Rights Data Analysis Group. She was a founding member of the executive committee of the ACM Conference on Fairness, Accountability, and Transparency. This is where I know most of her work from, and I'm very excited about that work. Her research focuses on the responsible use of algorithmic decision-making with an emphasis on the evaluation of models for harmful impacts and mitigation techniques. In the past, her research has focused on the unfairness of predictive models used in the criminal justice system. So as everyone knows, we have an hour for the talk. We have a mixed audience here. So the format we typically use is people are welcome to ask questions of clarification during the talk. And we ask that you hold your longer questions until the end. You can put your questions into the chat and I'll moderate that. Or at the end, you can use the raise hand feature on Zoom and ask your question yourself. So without any further ado, I turn it over to Kristian. Thank you.
Thank you so much. Let me just pull up my screen here. 1 second. And where's that play button? All right, there we go. So hi, yeah, thank you all so much for having me. It's really great to see, you know, some familiar little faces in the screens, and also really cool to see people. I see that there's a group in person in a conference room there. So I hope you all are enjoying getting to see other humans in person. So what I'm going to be talking about today is a project called Closer Than They Appear, where we look at individual level heterogeneity in criminal justice risk assessment. And if any of those words are not familiar to you, hopefully by the end of this, all of those words will be familiar to you. So I'll go through what all of that means shortly. But before that, I should mention that this is work I did with James Jandro, who did a lot of the computation, and David Dunson. Great. Okay, so I guess my slides are moving. Okay, there we go. All right, so one of the words I said when I set this up is risk assessment, or risk assessment instruments, which you may see me abbreviate as RAIs going forward. So these are models that are used throughout the criminal justice system in the United States and elsewhere to make predictions about contextually relevant outcomes given covariates. So if you're in machine learning, statistics, or any field that uses any of those tools, you're probably fairly familiar with at least the general setup in that box sort of in the middle there. So we're just trying to estimate the probability of some binary outcome y given covariates x. So we're just estimating some function f of x to estimate this probability that y equals 1. So in the context of criminal justice, usually y represents something like a failure to appear, FTA. So that would be if you're released before your before your trial, for example, that you would fail to appear for future court dates. Outcomes like whether the person is rearrested or whether they're rearrested for a violent crime. And I've put failure to appear here in bold because that's the one I'm going to be looking at today. Though I think the methods that we're talking about here would be applicable to you know, predicting outcomes that are relevant, the other sorts of outcomes as well. And I imagine the results would be similar. For the X, the covariates that go into these sorts of models, typically they're things like criminal history, employment status, residential stability, past failures to appear, sometimes demographics like gender or age, mostly age, and sometimes interview questions. And so this is sort of just a caricature of what these models look like. Not all of them have all of those different features you could. There's usually some subset of them, and I'm sure there's some instrument somewhere that I'm missing some of the features that go into it. But more or less, this is what these sorts of models look like. One thing I mentioned is that f is often constrained so that it is some sort of understandable function. maybe something like you have integer coefficients on each of the features that go into it, something like that. All right, so in practice, how are these used? So often what will happen is when they're building the model, they will come up with these predicted probabilities. Those in this previous slide here, those probability y equals 1, maybe say p, just call that p, that's we're going to call that later. And then we'll bin that. So those p hats are the estimated probabilities of the outcome we're talking about. And then those will be binned. So in this case, we have if an individual's p hat is say greater than 0.3, they're in the high risk group shown in red. If it's between 0.2 and 0.3, maybe in the orange group or medium high, between 0.1 and 0.2, yellow, medium low, and the green area there less than, I think that's 0.1 is green. And by the way, this is just an artificial sort of hypothetical example. These numbers I've just sort of pulled out of thin air just to illustrate what this sort of process looks like. And so really it's these groupings that in all the cases that I've seen are used to help inform decisions about what should happen to somebody at whatever stage that this sort of model is being used, not those sort of raw p hats or the estimated probabilities themselves, these sort of which group the person falls into. All right, and so since we're talking about policy, how are these actually used as a policy? They're used in a variety of ways. Here's one example. So this would show, this is a matrix, a decision-making systems matrix where you would have two different groupings. So you could imagine that in this slide we get, say we have 4 groups here, pretend we have 1 through 6 groups here. That would make up the x-axis, and then a separate prediction would make up the y-axis. So in this case, suppose this is a prediction of FTA, and you are in the green, maybe you're in group 2, we'd find where you are in the second row there, and then there's maybe another model running in parallel, and you're in, say, group 4 for that one. Maybe that's predicting something like rearrest, which in fact is what's being shown in this. So if you were predicted as a 2 for failure to appear and a 4 for rearrest, then we'd find that spot in the matrix that's yellow. I wish I could point. If I were in person, I were, but I trust we could read this. And you'd be in the yellow group there, which would be, I believe that sort of minimal supervision upon release. So this would be used at the pretrial stage, this model. So essentially when someone's arrested, this sort of model would be run, and then they would end up with this final grouping, this OR minimum here, which would be a recommendation for how much supervision they should get prior to their case being disposed. And so you'll note that again, this sort of jives with what I just said a second ago about those groupings. So on the green end here, these are sort of the people who have those lower predicted probabilities. In this case, the recommendation is basically let them go without conditions. Yellow is a little bit more conditions. Orange is a little more conditions beyond that, and then red is release not recommended. So those are the people for whom this tool is recommending the judge actually not release them prior to their trial. And I would note, just as an aside, just to sort of set the stage for how important these sorts of decisions are, what happens to someone prior to their trial has consequences for the outcomes of their trial. So there's been a lot of work over the last few years looking at the causal impact of, say, setting bail, which would be an impediment to them actually being released pre-trial or being detained pre-trial, and has found significant increases in the likelihood of being convicted and other sorts of long-term outcomes for the person. So these decisions are really consequential for the person being judged at the time. Though I would say that in all but one case that I've seen in these sorts of pre-trial tools, these groupings are really a recommendation and not a final decision. I've only seen one case where this is even approximating something like a final decision. So this is just going into, say, a judge's decision-making process, their internal mental decision-making process about how the person should be treated prior to their case being disposed. All right. So if you have been following the sort of algorithmic fairness, accountability, and transparency in machine learning, specifically in the computer science literature over the last, let's call it 6 years at this point, you're probably familiar with these models. Like, you've probably heard of them, and that's because they are one of the standard types of models that people usually talk about. In that first sentence in the paper, models are increasingly used in high stakes situations to make decisions about individuals, including in criminal justice, blah, blah, blah. This is usually the example people are talking about. So if you've been following that literature, you've probably heard about it. And in particular, you've probably heard about this article, Machine Bias, out from ProPublica, where they released a data set showing that the false positive rate for people who are white who were judged by one of these tools was about half the rate as those who are African American in their data set. I'm not going to go deeply into this because, again, if we've been following this line of work, and this is at this point 6 years old, we're probably familiar with this, but I'm really just pointing this out to sort of draw some parallels. So this notion of group fairness, essentially that the model performance for each groups ought to be the same, and when they are the same, that is the state that is defined more or less as fair, is sort of one of the paradigms that people have been thinking a lot about over the last several years in computer science when it comes to building fair models. And this is, I wouldn't say attention, but it's sort of a complement to other ideas about individual fairness, which is essentially that people who are similar should be treated similarly. So on the left, we have these ideas of group fairness. Again, if we group people up by their characteristics, the model should perform equally or approximately equally for each of those groups. And that's pretty reassuring about groups, but not especially reassuring about individuals within groups, that any individual within that group is, say, treated justly or fairly. And again, sort of the parallel to this is individual fairness, where the idea is to sort of abandon the groups and start thinking about people who are similar should be treated similarly. Of course, the difficulty with this, if you've been following this, is defining what similarity means and having that be sort of a contextually aware definition of what similarity looks like. All right, so I'm done with that. I'm just sort of setting the stage here to let you all know that this is something that we've probably heard about if you've been following this. And then we have these sort of two parallel ideas about fairness, group and individual fairness. Okay. And so when I came to this problem of thinking about RAIs more deeply, not sort of in the more theoretical or methodological sense, but really digging into what people have been talking about in the RAI literature, I actually found that there is a parallel debate that had gone on, I think starting in roughly 2004 in the risk assessment literature. And it goes something like this. The groups there are not, so in this case, keep in mind the groups in this case were something like race. In this case, the groups we're talking about are those groupings that I've told you. So they're the high risk, medium, low risk, and low risk groupings. But there really is this interesting parallel where people, and I think it was 2004, 2006, that time period, there was this sort of back and forth among researchers about whether when you take those groups, whether the probabilities that come out of these models pertain to groups or individuals. So backing up again 1 second, once people are assigned to groups, what is usually reported is the average rate of the outcome within that group. So if you were to take all of the people who've been assigned to that red group and say the average rate of failure to appear was, in this figure, I think it's about 0.35, then we'd say for people in that group, their likelihood of failure to appear is 0.35. And so really the debate was about, okay, so do these probabilities, the sort of average within group, do those pertain to individuals within that group? Or do they pertain to just the group as a whole and it has nothing to do with the individuals as individuals? And moreover, even beyond sort of what we've been talking about in the computer science literature, how do we characterize our uncertainty about, about whatever it is we're talking about, whether it is group probabilities or individual probabilities? All right. So if we're comfortable just saying, okay, they're group probabilities, they refer to a characteristic of the group as a whole, not individuals within that group, then statistics is, there's fairly well established, and by fairly I mean like extremely well established ways to talk about, our uncertainty about group averages. That's sort of stats 101. And so what we might do, and in fact, what often is done when thinking about uncertainty about these group averages, is do something like create confidence intervals around that group average. And so I've made a few confidence intervals here, one in black, one in gray. And something interesting about this, if you've done your stats 101, this should be fairly obvious. But if we were to make these intervals using 100 individuals, the intervals would be the gray ones. If we did it using 1,000 individuals within each group, not changing anything about the underlying data generating process, it would be the black one. So we can become more and more certain about that group average as we get more and more individuals. But again, that might not tell us that much about individuals within that group. And typically what people look for when they're doing this sort of uncertainty quantification is that these intervals don't overlap. That's one of the things when they do these validations, they're looking for, okay, these groups are actually different. We can, maybe reject the null hypothesis that the rates within the different groups are the same by looking at overlaps among these confidence intervals. But again, just sort of going back to that sample size issue, that's really telling us, these intervals are really telling us, more about the sample size used in our study than it's telling us anything about how variable individuals within each of those groups are. That despite the fact that I do think, just having heard people that, I've spent something like 5 years hearing people talk about this, talking with people about how these are used. I do think there's this tendency to interpret these group-wise averages as pertaining to an individual. So if you're in that high-risk group, group 4, saying, okay, well, the average within that group is 35%, your probability is 35%, and we're very certain about that probability, even though, again, there might be some differences for individuals. But before I sort of go off on that tangent, I want to talk a little bit about why these group probabilities are reasonable things to look at. And I'm not saying that people shouldn't be looking at these at all, right? So from the point of view of a policymaker, suppose you wanted to actually build one of these models and instantiate it as your policy for who's released, who's not released. You might actually want to know something about those group-wise averages. It might have something to do with planning, for example. Suppose your policy was everybody who's in groups 1, 2, and 3 is released. You might want to have some uncertainty quantification about what proportion of people you would expect to miss those court appointments so that you could plan accordingly. That's, of course, doing things like assuming that there's no sort of drift over time, but in any case, that would be a reasonable thing to think about if that were your primary concern. And you might, of course, want some uncertainty about that. How certain are we about the proportion that we would expect to miss under, creating this actual policy of releasing, say, groups 1 and 2 or 1, 2, and 3? And you might actually want to know, on average, are these groups actually different? So this sort of traditional approach to thinking about uncertainty quantification in this context, I think makes sense if that's where you're coming from, if that's the direction you're coming from. All right, but then let's take a step back and think a little bit about individual probabilities instead. So before, what I showed you were intervals that were talking about how uncertain we are about the average within the group. We could have these two different scenarios that would give you the exact same intervals that we saw on the previous page. So we could have a situation where everybody's individual probability, you can think of that as everybody has their own individual coin with its own probability piece of I is the ith individual. They flip it and that determines whether they're going to show up. So those probabilities could be distributed very tightly about the group average. That's what you're seeing on the left with the small, right? So that the gray distribution is just the distribution of probabilities, the parameters pertaining to each individual's coin for people within each group. Or we could be in this situation on the right with large variance of that distribution of piece of i's, right? People are highly variable in terms of their actual probability of showing up, for example. And so why might we want to know something about this instead of just those group averages? And I'm not even starting to talk yet about quantifying uncertainty about this. These are just sort of two hypothetical distributions we could think about. So if you were a judge, you might actually want to know, how relevant is this risk label to the person standing in front of me about whom I have to make a decision? At that point, I'm making a decision about an individual. I'm not making a decision about a group. And so while this group information might be relevant to me, it might also be relevant to me to know whether I find myself in sort of the left-hand scenario or the right-hand scenario, right? Is this very likely to characterize this person very well, this group average? Or is this an average across many people and each individual within that group is not an especially great characterization of them? And of course, for people who've been arrested and are being evaluated by one of these models, they're probably interested in the same thing. Is this risk label really likely to grossly mischaracterize me? In particular, if I am very likely to show up and I know that and I end up with this high risk label, that could be a problem and I'd like a way to convey that. And so this is really sort of what the argument was. Should we be worried about the group in light of the fact that this could be the case? And again, just sort of going through these scenarios again, in scenario 1, where we have this small variance, all individuals in group 4 have probability roughly 0.35 of the outcome. And so, perhaps, I'm saying perhaps here, I'm not sure this is necessarily like normatively the right judgment call, but perhaps a judge would be comfortable, say, detaining people whose personal probability is 0.35, and in that case, using that group as a signal for what everybody within that, using that label as a signal for what that individual's probability is, would perhaps make sense. However, if we find ourselves in scenario 2, this large variance scenario, individuals in group 4 have probabilities that are widely varying, even though the marginal rate in that group is about 3.35 also. And so in this case, perhaps having a 25% chance of detaining a person whose probability is less than 0.2 based on their group label is unacceptable. So if you're in the scenario on the right, if you say, okay, I'm just going to detain everybody who's in group 4, that high risk group, you'd have a 25% chance of detaining people whose personal probability is less than 0.2, which in this hypothetical example is less than the average probability in the population. And you might find that morally unacceptable. All right. So unfortunately, when we only have one observation per individual, we actually cannot tell, like mathematically, we cannot tell these two scenarios apart at all. So if you were to draw, say this is your generative model, you draw samples from the left, you draw samples from the right, you're going to get basically exactly the same data. And if you were to do the group-wise inference, you'd get exactly the same thing you saw a couple slides ago. So where does that leave us? This was sort of where the debate in the risk assessment literature was left circa 2014. It's like, okay, well, we can't really tell the difference. I'm going to actually come back to that slide in a second. So, so what could we do if we can't actually tell the difference? If we mathematically know we can't tell the difference, what can we do? Well, we can sort of fit the standard model. Perhaps F is, we're just fitting a logistic regression here, and we can assume there's no individual level heterogeneity. So we can make a model where we have F is, X transpose beta. That's essentially just a linear model, maybe a generalized linear model where we have this F, which is transforming it to a probability scale. There's nothing in this that has anything to do with individuals, but we certainly can get uncertainty quantification for the beta hats, push that through to uncertainty quantification about our PIs, and get some sense of uncertainty quantification about those PIs. But we have to keep in mind that when we do that, we're getting uncertainty quantification conditional on a model that has already assumed there's no individual level heterogeneity. And so we've sort of assumed away the interesting part of the question. Like, while we can sort of mechanistically get intervals, they don't, I think, satisfyingly have anything to do with individual probabilities, because there's nothing about this model that's specific to the individual. The other thing that we could do in this case, and this is largely where things were left, I think around 2014, was we can kind of just assume that there's not a problem. So we can assume that the empirical group-wise rates are approximately accurate representations of each person's individual probability. So if P sub G is the group-wise average, just assert that P sub I, the person I's individual probability, is about the same as the group-wise average, and kind of go from there. And there are things you can do. You can do calibration checks. You can do all of these things that give you some evidence that that you're at least not totally off base about, how things are going, but you're basically assuming you're in the small variance scenario and not the large variance scenario, because you can't know. And that's, I guess, pragmatically all that you can do if you want to use one of these models and apply it to individuals. So that's largely where it was left. We can't know. Well, there's some things we can do to make sure the model is at least not terrible. And then from there, we just have to sort of assert that this is true or hope that this is true. All right. So let's talk about what we could do if we did have multiple observations per person. So here's a really simple idea, and I'm not necessarily saying we should do this, but here's a simple idea. So now we have y sub ij, that's the ith person's outcome on the jth observation on which we observe them. We'd say, okay, that is Bernoulli of P sub I. So each person, this is basically the model I told you before. Each person gets their own individual coin, the ith coin, with probability P sub I coming up heads, and each time they flip that coin, and we observe a y sub ij. All right, and then we would get their P sub I after the jth occasion. We sort of after the jth time we observe them, it's just sort of the empirical average over all of the previous times that we've observed them, right? And so this is a really simple model, right? We just take, say, the average rate in the past that you failed to appear for court, and that's our estimate of you going forward until we get more information. I think some pros are that it kind of takes seriously the idea that before the law, you should be judged only on what you've done, not what others have done, which is something I've heard come up a lot when people are sort of critiquing these types of RAIs. Essentially, you're using data from what a lot of other people have done, and now you're judging me based on that data, via this sort of, the vehicle for that, right, is the model, but that's essentially what's happening. You've seen what other people have done, and now you're judging me based on that. At the very least, that takes seriously that idea. Some cons to this approach is that I don't think it would work. If you actually wanted to use one of these models to divide people into groups, I think that's just it's not realistic. You would require many observations per person before you could estimate each, that P sub I with any reasonable degree of certainty at all. You'd have to observe somebody so many times that you're just kind of, it's not especially useful to inform decision making. But I would say there are some pros, at least conceptually, that you might want to consider for doing something like that. Another thing you could do is you could be Bayesian, which I'm always a fan of being Bayesian. So one thing you could do is sort of pop out that p sub I here and replace it with this phi of theta sub I, and that's maybe a little bit of foreshadowing of what's to come, but you could just in your head think of that theta, sort of that phi of theta sub I as the p sub I there. And you could model this with a prior. So you have your theta sub I, and that has some prior distribution there. And then you could do updates based, you could do sort of a Bayesian update of an individual's probability, right? So you have some prior on what the individual probabilities are distributed like, or what an individual's probability is. You observe those y sub ij's, and then you do a Bayesian update. And so you have some prior, maybe it's fairly wide like you see on in the left figure down there. You observe that they haven't failed to appear at all, and then you update that using Bayes' rule, and you get the distribution on the right. All right. I think some pros to this, it's an appealing and coherent framework for interpreting distributions over P as beliefs. That's not just for this sort of RAI setting. That's a generally true statement about Bayesian statistics. I think it's appealing conceptually and philosophically. But I think from a practical standpoint, this type of, you can think of this also as regularization via the prior can give more reasonable estimates. So you don't end up, if you see that somebody didn't fail to appear the last 2 times, you say, okay, there's a 0 chance. That probably doesn't make sense. And so you use this prior distribution kind of to regularize and get more reasonable estimates. Some cons to this is that it's sensitive to the prior. So, if you choose a different prior, you're going to get a different answer in terms of your posterior beliefs about an individual's probability after you've observed, say, the 0, 0, 0, 0, which I think could make it hard to justify, because one of the major reasons people want to turn to these sorts of models, or have been for, it's not even a recent innovation, it's been happening for a long time, is to make more objective decisions. And because the sort of objectivity is one of the major selling points of RAIs to begin with, I do think it can be a little bit difficult to convince people that a Bayesian approach, and especially one using such a simple model where it's going to be highly sensitive to the prior, would fall in line with that objective to make things more objective. I just used the word objective twice to do different things, but all right. And so we could learn the prior, which I think gets us a lot closer to the direction I'm going, and I think something that makes a little more sense. So we again are observing our yij's, they're Bernoulli, we have this theta, we have our prior on theta, but then we actually learn the parameters eta, which are the hyperparameters. So we essentially learn the prior. So in this case, the prior sort of represents the population, the distribution over the population distribution of p sub i's, and we try to learn that sort of iteratively as we go along. Pros, again, we still have that nice Bayesian framework, so we can, we get sort of the philosophical properties that make it convenient to interpret things like uncertainty about probabilities. And I think this is a nice compromise, because the data informs you about how much other people's influence should influence your estimates of p sub I. So if what I learn over time is that everybody's p sub I really is between 0.2 and 0.3, then I can use that information to update about you, but I've learned it from the population, right? Of course, a con for doing any sort of Bayesian inference like this, and especially when we start specifying hyperparameters and specifying these more complex models, you're going to have disagreements about how to even specify the model, including functional forms for the class of distributions for that f of eta, that prior on the theta sub i's. All right, and so this gets us to the model that we actually use, which is just a slightly more complicated version of what I just told you about. So this looks a lot like what people do in practice, with one slight difference. So we still have our yij, the I person's outcome at the jth occasion. And we're basically modeling this with a probit regression. So if you've done logistic regression, it's very similar to probit regression, just a different link function. But it's more or less the same thing. If you were to take out that theta sub I piece, then this would just look like almost exactly like what people do. So if you block out that theta sub I, this is literally just a probit regression. It's just the standard thing. By adding in this theta sub I, we've added in an individual effect. So this is how much this individual varies above and beyond what their covariates you'd expect based on their covariates. So we can think about this as an individual sort of like idiosyncratic difference from the group-wise average. And we simultaneously learn these covariates beta, sort of the traditional regression setting, and these individual level deviations. So we can actually learn something about, okay, even though we've seen these covariates about this person tends to be a little higher or tends to be a little bit lower. And by doing this all in the sort of Bayesian framework, we can also get uncertainty quantification about those theta sub i's. So these theta sub i's have this random effect distribution, similar to what we just saw, this f sub eta. And of course, we need a prior on the regression coefficient, which we've chosen to be a fairly weak prior, but still within the range of the values that you would expect for something like a probit regression, because once you get out in the tails, then you essentially get zeros to ones. Yeah, I see it.
I have a question. Sure. And maybe if you're going to talk about this later, that's okay. It seems like one change here is you brought in the X betas. Like the previous slides, you're building a more and more complicated individual level models. And here you're bringing in the X betas, which seems like it's kind of taking information from other people to make judgments about you.
Yeah.
Do you see that as like a big change adding the X betas in?
Actually, I don't, because we still have the theta sub I in here. And so what we could estimate is this average. We could estimate, you know, from everybody what the average effect is based on these covariates. But if we estimate that these theta sub i's have large variance, then we still end up saying, okay, we don't know much about you as an individual based on your covariates, because we know that these theta sub i's vary very widely. So you can get an average, but then because we can actually quantify uncertainty about theta sub i's, our estimates of what we know about you as an individual, they do shift, you know, in the mean based on what other people have done, but we still end up saying, but we possibly don't know anything about you, because we can learn that we're very uncertain about an individual's shift. And we can learn, for example, that the population variation of those theta sub i's is large.
So if I understand right, it seems like you're kind of saying this is like a hybrid, like some things only look at group characteristics, some things only look at individual characteristics, and you're trying to, or some things are very using only data from this person, and this model kind of combines both of those, and it gives us the good properties of the one that only focuses on the individual with the benefits of pooling or averaging that come from including the covariates.
That's right.
Okay.
Yeah, I think that's a really good summary, and I might borrow that in the future. Since this is being recorded, I might just go back and steal your words. I can go back and look at that. But yeah, so if we learn, for example, that the theta sub i's don't vary at all, say we learn the variance is 0, which we're not going to learn 0, but suppose we did estimate it to be exactly 0, then we've learned that we really are in the situation where those covariates tell us everything. We're essentially in that small variance scenario, right? Whereas if we learn that theta sub i's vary really widely, then we've learned that we're in that large variance scenario for the original setting. And so we can actually kind of learn which setting we're in and how much those covariates should tell us about you as an individual by including this additional parameter.
Thank you.
Sure. So just to go through really quickly some of the pros, you know, it does have this individual specific parameter. So I think it's defensible as having something to do with an individual probability. As we learn more about you, as we get more data on you as an individual, we can you can vary more from the group-wise averages, for example. And like Matt just said, it's a nice compromise. I think the data informs you about how much other people's information should influence estimates of P sub I, but we still do get to bring in, if that is useful signal, we still can bring in some of that signal from everybody else via the X betas. Again, we're still in this situation where this is going to require assumptions about F sub eta. So we're going to have some parametric assumptions about our prior on theta. And, you know, we could elaborate on this model a lot more. We don't have individual effects over time. So, you know, how much you deviate from the group average does not change based on whether it's the first time, the second time, the third time we've observed you, or whether it's Friday or Tuesday or anything like that, right? You have your own individual effect. And we don't have individual level betas, for example. These are all things we could do. One thing I will say, and I'll talk about this more a little bit later, is that one of the reasons that we've decided to do this really minimal change, again, really how we're changing from the sort of traditional paradigm is just adding in this theta sub I, is that we really wanted to see if we do the bare minimum to account for some sort of individual heterogeneity, does that change what we have to conclude about, you know, how these sorts of models should be used. So we didn't want to sort of throw the kitchen sink of changes at these types of models, because then, you know, it might be because of this. We really wanted to say, let's do the bare minimum and see what we conclude if we just, you know, do the absolute minimum to account for individual level heterogeneity. And so coming back to that random effects distribution, you do have to pick some sort of functional form for it. We picked two, normal and discrete mixture. These are samples from those priors on the left and the right respectively. I'm going to really just focus on the normal, but tell you, and you'll just have to believe me on this, or you can read the paper and see the results yourself, that substantively the results were very similar between the two priors, and so there's not really a need to show both results. Just keep in mind they were very similar, and also that these priors are actually really different. You can see that they look very different. One of the reasons we focus on the normal, the one you see on the left there, is because we have this parameter tau. And this is really convenient to talk about because it's the variance of those random effects. So basically, if tau is small, we're in that small variance scenario, and we can learn what tau is. And if tau is large, we're in that large variance scenario I showed you up front in those sort of introductory slides. And we have no such simple parameter on the right. So I'm going to focus on the one on the left, and we can talk about tau, but just keep in mind that this wasn't actually, it was actually less sensitive to this prior than I was expecting this to be. All right. And so for the first time that I've seen in studies of risk assessments, we had this really massive data set where we did have repeated observations of individuals over time. So we got this data from the Kentucky criminal justice system that covered June 2014 through December 2018. We reserved the last year as a holdout as is standard in this literature. So we had about 532,000 training arrests and 79,000 holdouts. For covariates, we had the ones that you see here. So these are the ones that I talked about up front, things like past arrests, some demographics, mostly age here, under 21, past incarcerations, past failures to appear, etc. And we were looking at that outcome of whether the person had any failure to appear during the pretrial period. So setup here is really pretty standard for these sorts of models. And we also had the other information, which isn't used in our modeling, but is used in our evaluation, which is which risk group the person was assigned to by a model that was actually running at the time. So when they were evaluated in real life, were they assigned to the red, green, orange, yellow, whatever, those sorts of groups in real life. All right. And so again, just to show you it's true, we did have multiple observations per person. Most of the people were singletons. So that's what's shown in the highest bar there, but we had many people who observed 2, 3, 4, 5, 6, and this is on the log scale on the y-axis. So we had several thousand people we observed, I think 6, 7, 8 times. So we did actually have enough data to estimate these sort of individual level effects, and even perhaps more importantly, the population distribution of individual level effects. And so here we're going to get right into the results now. And this is something that was important to me to show. I don't know how important this will be to you all, but this is our posterior distribution of tau. That's that variance parameter for the random effects. And you can see that it's fairly tight, around 0.45. And so at least qualitatively, I look at that and I think, okay, we're fairly certain about what tau is. That's a good thing. And we know it's about 0.45. All right. But one thing that we might want to think about is when we start talking about our posterior uncertainty about P, an individual's P sub I, we can decompose this into what I think of as the natural variability in P. So if we know the parameters, we know beta and we know tau, how variable are P? That's that first term. And our uncertainty about P also comes from our inability to estimate beta and tau very, very precisely. So if we have a lot of uncertainty about beta and a lot of uncertainty about tau, we might still be very uncertain about an individual's P sub I just because we don't know what those parameters are, right? And so I wanted to sort of test this. And so like how much of if we conclude the P's that our uncertainty about P is very high, how much of that is because we just can't nail down beta and tau, and how much of it is because we very precisely estimated that individuals vary greatly across the population. There's sort of two things. And so the figure on the right addresses that. The blue line shows what our posterior predictive distribution is for P. So what does our uncertainty look like for an individual's P? This is the median individual. I don't need to go into details of that. If we fix the parameters beta and tau at their point estimate, so their point estimate is their posterior mean. And what does that distribution look like if we take a sample from the full posterior? So we average over our uncertainty about beta and tau both. And essentially the answer doesn't change. So to the extent that we do learn that individuals vary greatly, or that we have a lot of uncertainty about an individual's P sub I, that's because we've learned that individuals vary within the population, not because we haven't been able to learn what beta and tau actually are under our model. Maybe that's not that important of a distinction for other people, but that was important for me to investigate. And I know I'm a little bit short on time, so I'm gonna really focus in on one thing when we start talking about group level results. And so that variable I mentioned where we know which group people were actually assigned to in real life, I'm going to use that and then look at how variable people are within those groups. Keeping in mind we could group people other ways. We could group them using our own model, keeping the size of the bins the same. We could group them using our own model and vary the sizing of the groups, things like that. And we did all of that, but I'm just going to focus in on what if we use the groupings that actually existed previously. And so that's all of these are going to be on the far left. So if we look at the groupings that were actually used under our model, we see we have fairly good calibration. So we have our P stars and Ps, you can sort of think those the same thing for now. We estimate the average rate within group 1 would be 0.1 under our model, and we get a rate of 0.08. That seems like we're fairly close, and we're fairly close up the board. So this is a sort of standard calibration study people would do when they look at these sorts of models. So out of sample on the right, in sample on the left, just looking at out of sample calibration, essentially, how close is our model to estimating those average rates within groups. And considering we're using a slightly different time period, right? We're using the end of the data versus the beginning. I feel like this is definitely within the range of what people would say is a reasonable level of calibration. But this is where things get interesting because we can actually get the full posterior distribution of P sub I for people within groups. So we can say, okay, conditional on being in group 6. So conditional on the fact that you were assigned to group 6 at the time of your arrest. What is our posterior distribution of PIs for people within that group? And that's what's shown by the black distribution here. So again, we fit this model. We're sort of averaging over all of our uncertainty about the taus, the betas, et cetera. Then we can say, what is the posterior distribution of P sub I conditional on assignment to each of the different risk groups in reality? And we end up with these really wide distributions. So in a nutshell, we find we've actually estimated from the data that we're in that large variance scenario and not in the small variance scenario. Because we have multiple observations per person, we can estimate that tau parameter, we can actually solve this issue that's been sort of plaguing, I think, risk assessment for years and years and years. Like, which one is it? We always have to assume that it's one or the other. We can say, okay, at least based on this model, it seems that we're in the large variance scenario. Not that it's binary. It's of course a spectrum. I think I saw Matt's hand.
I had a question. So this is the PI, or this is the estimated probability, or it's the individual specific risk parameter, the theta?
Okay, so this is, suppose we have, so for each individual P sub I, we have a posterior distribution for P sub I, right? So we say take a sample from a person who's in group 6, take a sample at random from someone who's in group 6, and then sample at random from that person's posterior probabilities. This is the posterior probability of P sub I averaged over individuals who are in group 6. Does that make sense? And group 5, group 4, group 3, group 2, group 1. I'm focusing on group 6 because it's at the top, but
yeah. Okay. So right. There's like there's a sample of a person and then a sample from the posterior. And this is many times that process.
Yeah.
Okay.
So if all we know is that someone's in group 6, what is our posterior uncertainty about that individual's probability? Well, it looks like that. Like that.
Okay. Yep.
Of P, given only that we know that you're in group 6. And so I think a notable characteristic of this is that there's considerable mass down pretty low. And so just because you're assigned to group 6, where we would say, okay, the average rate in group 6 is say 0.3, it looks like in this data set, there's a substantial portion of that population who could have probability, say down closer to 0.1, which is closer to the nominal rate for people who fall into group 1. So there is quite a bit of overlap among these groups. And we can actually look at that overlap directly using these posterior distributions. So we can say, what is the probability that you were assigned to the quote correct group, where correct group just means that your individual P sub I is closest to the group average for each of those groups. So if you're always assigned the correct group in this case, there would be a diagonal bar going up and to the right in each of these figures. In fact, we see there is basically what I said visually in the, just by sort of visual inspection in the previous figure, there is quite a bit of overlap. Just because you're assigned to group 3, your probability, there's a decent chance, for example, that your individual probability is more similar to the nominal rate for someone for a different group, not group 3. And we found that, our posterior probability of being in the quote correct group, if you based on the groupings that were used in reality, was about a quarter. All right, and so now we can sort of talk about what could we do with these individual level intervals. So each of these intervals you see going vertically, each of these gray bars or blue bars shows an individual's posterior interval for PI. So one thing I've done here is I have ordered them in kind of funky way, but you can just sort of see they're sort of ordered going upwards. So the people whose intervals are on the right are centered higher than the people who are on the left. So one thing we might want to do if we want to say, okay, we want to make groups and we want to be able to say that individuals within those groups are different. Suppose with high certainty, suppose we did something like this where we draw this line here, this black line at 0.25 and say everybody who's above the black line, the lower end of their interval falls above it. And so they're in the high risk group, everybody whose upper end of their interval falls below it is in the low risk group, and those groups aren't really overlapping at all in terms of the individuals within those groups. So we can say something and say like, the individuals within these groups are actually different. I think this is actually kind of nice, but the one issue with this is that you really can't flag that many people. I think it was like 5% of people combined were in either of those groups. And given that the whole purpose of this exercise was to, sort people into different groups, if you can really only say anything about 5%, maybe it was 7, it was something really small. But then for 95% of the people, you have to say, we don't know, we can't really disentangle them from the low or the high. I'm not sure how much utility this has for people who would actually like to use one of these models. But it is an option. Another thing we could do, and I actually really like this, is instead of focusing on point estimates for individuals, start focusing on our uncertainty about those individuals. So this shows our posterior probability, the individual I's personal probability. Sorry, this gets a little confusing because we have a few layers of probability here. So the probability that P sub I is greater than some threshold C is greater than H. So where H is shown in each of the different squares, and C is shown on the x-axis. So this would say that if we wanted to say we wanted to be, I wish I could point again, but if we wanted to have at least 75% certainty, we wanted to flag all people with 75% certainty whose individual probability fell above, say, 0.3, you'd go up, you'd sort of find 0.3, you'd go up to the upper left quadrant and look at the height of the bar there, and we could see that we could flag about, I think that's a little less than 10% of people. So there's about 10% of people who we can say with statistical certainty 0.75 that their personal probability exceeds 0.3. I think I said it right that time. And the reason that I really like this type of approach instead of focusing specifically on point estimates is I think it's consistent with the values that we should wait for enough evidence to accrue about the individual before flagging them. So instead of just relying on the point estimate, okay, we've seen a lot of people that have similar properties to you, we have a lot of uncertainty, but on average, we think you're going to be high. We'd actually have to observe somebody many, many times, become very certain about what their individual level shift is to then be able to say anything. So even if we see somebody the first time, group-wise information says, okay, on average, based on those covariates, you should be high, but we don't really know much about you. We need to learn more about you. And once we've sort of reached some standard, we could flag that person for additional review, perhaps. I think, de-emphasizing the point estimates and more emphasizing something like individual level uncertainty would be really helpful for that. Again, once we start talking about kind of classical, or I guess, conventional ideas about what statistical certainty is appropriate, 0.9, 0.95, 0.99, for example, then we're again in this situation if we only want to flag people, or we can't flag that many people if we pick reasonable threshold C. So the marginal rate in this data was about 0.2. So say we want to flag people who are pretty sure their individual rate's above 0.3, we're back down to this sort of thing where we're only flagging a very small proportion of the people if we want to have sort of, normal, say alpha equals 0.05 or, whatever the sort of standard statistical threshold is for certainty that's appropriate. And I realize I do think I'm over time a little bit, but this is the last thing I want to say. And that is that the way this model is set up, what we found that, individuals are highly variable within groups, that we have a lot of individual uncertainty, that there's a lot of heterogeneity, was not a foregone conclusion of our model. And then I want you to focus in on the figure on the right. we have here what the interval length is on the log scale, sorry, just so you can fit it all on here, as a function of the number of times that we've observed an individual for different values of tau, where the value of tau that we estimate from the data, again, tau being the population distribution of individual probabilities, is 0.45. And we see here, in order to get and you're going to have to do some mental math here, but I'll just say the words out loud. In order to get an interval that's say length 0.1 or less, you'd have to observe the individual, I think, about 100 times in order to get, say, okay, they're between 0.2 and 0.3 based on the tau that we've observed. However, if the reality were that there were not much population level variability, that tau were actually much smaller, there was much smaller variation around that group average, say tau is 0.1, like the dotted line, you could really observe somebody just a couple of times and get an interval that's very small. That's sort of a property of the model. And so again, I just really want to highlight that finding that we can't really know anything about individuals using this model, we could have concluded the opposite if the data had told us that. If the data had told us that tau is small, we would have actually concluded the opposite, that the signal from the betas or from the sort of group-wide, the sort of traditional regression function is actually telling us a lot about individuals, and we can get realistic or reasonably small intervals about individuals. The fact is just that the data told us that there's a lot of variation among individuals, so it wasn't a foregone conclusion when we set up the model. All right, limitations. I think it's always important to say this sort of thing. We did have to pick a random effects distribution. The results are qualitatively similar using different ones. We still used a linear model. We tried other things like random forests without the individual level heterogeneity. It's a little harder to build that in. And the predictive performance, because we have not that many covariates and they're all categorical, and it wasn't that much different. So whatever, it wasn't very much different. And our random effects were constant across time. So we didn't have individually varying regression coefficients, anything like that. And I spoke to this a little bit before, but we really wanted to make the minimal change and say, if we make the minimal change, how does that have to change what we concluded about how appropriate this is to use to judge individuals? And my intuition, based on years of being a statistician and fitting, hierarchical Bayesian models, is that if we had added additional complexity or we'd elaborated on this model to, account for, say, changing or, temporally evolving regression coefficients, something like that, that additional complexity would really only increase our posterior uncertainty. So I think that would exaggerate the results we've already found. So to conclude, these sorts of models are used to assign labels to real human beings, and those labels affect the trajectory of their lives. So what we've done is we've done the bare minimum to account for individual variability that's not accounted for by covariates. And we found that there's considerable between individual variability or heterogeneity that swamps what little signal there was in the data. We'd also found that we'd have to release people an unrealistic number of times before you could have small intervals. That 100, you have to release them like 100 times before we'd have an interval length of, say, 0.1, given the signals that we currently have. So given the covariates that are currently available. And just sort of maybe to put too fine of a point on it, is that these groupings may be useful at the aggregate level, things like planning, but when it comes to assigning it to an individual and saying, okay, this individual will or will not do that, or that this is this individual's probability or not, they offer very little information about individuals. All right, so thank you.
Thank you.